Hello, everyone. Thank you very much for attending this meeting. My name is Carlos Rodriguez. I work for HUESKER Geosynthetics. The content of the presentation is going to be an introduction. It includes the motivation of creating this system. I'm going to talk about RinTrack, that is the system, a case study, and we have a summary. So, HUESKER was created in 1861. We started creating and fabricating geosynthetics for different areas, as you can see here. One of our most popular area is earthworks and foundations, but we have products for road and pavements, environmental engineering, hydraulic engineering, and we have other many services. As I mentioned, we have different products and different alternatives for different areas. Today I'm gonna talk about geotextile-encased columns that we put it in the earthworks and foundations area. So basically, what happened with very soft soils is the foundation soil doesn't have enough bearing capacity. So the embankment fail under the deep-seated general shear failure, or what we call as, or we know as global stability. So we can see this material was displaced under the load of the new embankment, and it fails. And even if we don't get the failure, we are gonna get large deformations, vertical deformations, as we can see here. So there are different solutions for this problem. We can have a total or partial soil replacement. We can have a construction methodology adapted to the soil conditions, vertical drains. We have soil confinement, soil improvement, and we can create a load transfer platform. So now I'm gonna continue with the system. RinTrack. RinTrack was created for very soft soil, so I like to divide this slide in 5 different elements. The first one is for embankments. This system is only for embankments or dikes. The soil should be very soft. It should be too soft. We talk about less than 15 kPa or 2.1 psi. Or if your technical report is based on SPT block counts, we say that we should have less than 5 SPT block counts. We have a firm layer. This is an end-bearing system, so we need to transfer the loads to the firm layer. And now we have the column. So we have geotextile-encased columns, high strength, high modulus geotextile. So basically, the columns will transfer the loads, the vertical loads, from the embankment to the firm layer. And the last element is a horizontal reinforcement as well, high strength, high modulus horizontal reinforcement that is gonna distribute the loads on top of the columns, and is gonna increase the global stability. The key of the system is we fabricate this geotextile without any seam. We don't have any seam. So any type of seam, any kind of seam in geotextiles is gonna create a weak point, and we don't want a weak point in the system like this one. So the design is for the final state. We consider a uniform settlement between the columns and the soft soils. We don't consider any settlement of the firm layer. The column is incompressible. It means the volume at the beginning, the volume of the column is gonna be at the beginning. It's gonna be the same at the beginning at the end of the construction, and the column fill is plasticized. So we are considering like we reach the peak of this material. So for the assumption, we are assuming like most of the loads are carried by the columns. So here we can see a representation of our columns in your left. So a representation of the columns and a representation of the subsoil. We are assuming like arching is creating, and we have like this area ratio. So each column is improving a certain area of material, and we can calculate the improvement area ratio. For calculating the area ratio and the strength of the material that we should use, we use this formula for each layer, but we have our own software. So with these inputs, we can get what you see here, the results. So basically, based on this area ratio, based on the strength of this material, in this case we have 100 slash 500. 100 means the longitudinal strength and 500 the lateral strength. And we can see what's going to be the behavior of this. So we can produce also like a parametric study for different type of materials, for different type of strengths and raw materials. We can know what should be the area ratio and what should be the settlement that we are going to use. In terms of installation, we have three different methods. We have displacement method is the most common one, replacement, and vibrofloat. The displacement method is a tube. It has a element that is gonna in the toe. It's gonna displace the material. Since it's too soft, it's gonna displace the material. Then we are gonna introduce the geotextile, and then we are gonna start filling the column with sand or gravels. We can use local materials. This is another type of installation. This is the most recent one. Is a vibrofloat. Using this type of equipment. One of the biggest concerns here was the damage of the geosynthetic. So we have created this type of sites in which the column was installed, and then we excavated and checked what was the damage. How was we know the tensile strength after and before the installation, so we can calculate what is going to be the factor, the reduction factor to use for our design. We have a case study, so we need like a vertical load to activate the system. So here we created this site. It has 12 columns, and on top of the columns, embankment was installed, was built. And then 6 containers full of sand were put on top. The idea was to get the failure of the system. This was like a sketch of what was happening. We never found the failure, so we needed to include more, to add more load on top of the embankment. But what's really important is what we got in this graph. So in the vertical axis we have the loads, and in the horizontal axis we have the different days. So we can see vertical lines that are representing different stages, so different increments of loads. And we can see in red what is the load that is being carried by the columns. In green, we can see what's the load that was carried by the soft soil. This is a case study. The idea was to extend the facilities of this facility. The only option goes to the north, and you can see what are the conditions on that side. So basically, this was the existing facility, and then they needed to extend it in this area. The idea was to create a dike with this area, and then fill it out with sand or any type of material, getting this result. So the initial idea of solving this was to create these two barriers, so that you can see in the first figure of your slide. So the idea was to create these hydraulic barriers and then start building the embankment. But instead of that, a ring track or our system was used, and with different geosynthetics, the problem was solved. So the dike has a 1.5 mile. It was long, and we used GECs from 13 feet to 46 feet. This was the idea. So 60,000 columns were used, and most important was the time that was saved. So instead of using like 3 years of construction, the time was reduced to 1.2 years. Another we can customize the design. So in this case, where the loads of the embankment were not too high, we use a lighter material. So that's gonna save money in the project, and this is the final result. Thank you for your attention, and let me know if you have any questions.
Anybody have any questions for Carlos? Thank you.